Hello and welcome back. In today's video, I'm going to be going over the 2026 AP Calculus BC free response questions. So let's start. We're going to be starting with question 1, and questions 1 and 2 are the questions where you're allowed to use a calculator. So in question 1, we're given that male birds of a certain species arrive at a nesting area over a 30-day period, and the rate at which the male birds arrive at this nesting area is modeled by the differentiable function m of t. And in this data table here, we have selected values of m of t for given values of t. So let's start with part A. Approximate the value of m prime of 7.5 using the average rate of change of m over this interval. And we have to include units in our answer and show the work. Well, what is the average rate of change? Let's just imagine a function like this, for example. And this is going to be m of t. This is not the actual function m of t, this is just for the example. If we drew a line like this between 10 and 5, well, the average rate of change is just the slope of this line. So how do we find the value of the slope of the line? It's the change in the y value divided by the change in the x value. So in order to do this, we're going to be writing m prime of 7.5 is equal to, let's expand this, m of 10 minus m of 5 divided by, and well, 10 minus 5 is 5, so we can just write 5 here. And what is m of 10 and m of 5? M of 10 is 16, m of 5 is 7, this equals 9. So our final answer is just 9 over 5. But is it our final answer? We don't have any units. Remember that m of t is measured in birds per day, and m prime of t is the derivative of m of t with respect to time. This means that the units for this are going to be birds per day squared. And there you go, that's the answer for part A. Now part B. Use a midpoint Riemann sum with the three subintervals 0 to 10, 10 to 20, 20 to 30 to approximate this value and show the work that leads to your answer. So let's think about what Riemann sums are. I'm gonna draw here. So if we have a Riemann sum, it means that we're approximating the area under a curve. And how do we do this? We do this with the rectangles. So I could have a rectangle here, and so on. We add up the area of all of these rectangles to approximate the area under a curve. So here we're being told that we want to find the area from t equals 0 to t equals 30 of the function m of t using three rectangles. So the important part of the rectangles is we need to know the width and the height. And we know the width. All of these subintervals are of length 10. So 10, 10, 10. We know the width is always 10. But what's the height? That's what this is for. This is a midpoint Riemann sum, meaning that for each interval over here, so if we have this rectangle, if this is 0 and this is 10, your height is determined by the middle point. So the height value here is going to be m of 5. And so for the interval 10 to 20, it's going to be m of 15 times 10, and this is going to be m of 25 times 10. So let's approximate the integral from 0 to 30 of m of t dt. So the first component of our answer is 10 times, the midpoint is 7. So 10 times 7 plus 10 times, the interval is from 10 to 20, so the midpoint is 15, m of 15 is 6. Plus finally 10 times our final interval is from 20 to 30, the midpoint is 25, so 2. So this just gives you 70 plus 60 plus 20. This is 70 plus 80. This is equal to 150. But what is the units for this? We integrated the function for a rate, so birds per day, meaning that this is just equal to birds. And this actually ties into part B II. Interpret the meaning of this integral. Well, in the context of the problem, this means that approximately 150 birds arrived at the nesting area over the period of 0 to 30 days. So from 0 to 30 days, approximately 150 male birds arrived at the nesting area. So let's move on to part C. The rate at which female birds of the same species arrive at the same nesting area in birds per day is modeled by this function. How many female birds of the species arrive at the nesting area from time is 15 to 45? And this is where you're going to be using your calculator. All you're going to be doing is integrating this function, because this is the rate from 15 to 45, all you're going to be doing is integrating this function from 15 to 45. So I have decimals open here, so I'm just going to integrate 15 to 45 of 18 plus 16 pi over, sine of pi over 20 times t, sine of pi over 20, t plus 15. And this should give us the answer. Wait, no. There we go. So this gives us an answer of 641.859, and make sure your calculator is in radians mode when you do this. So this means the setup for the calculations is what I showed in the decimals here, and your answer is going to be 641.859, but it tells you to round to the nearest integer. And I'm going to round to 641, because if you round up, that's going to be 642 birds. You have 0.141 extra birds. That doesn't make much sense. So I'm going to round down to 641 female birds. And finally, part D. On the interval from 15 to 30, the difference in the rates at which the male and female birds arrive is modeled by some differentiable function m of t minus f of t. Now, is there some time t in this interval where d of t is 0? And the way we're going to be approaching this is the intermediate value theorem. Why? So the intermediate value theorem states that if I have, let's say, some value up here and some value up here, this is of a function, so there's a function like this, and this, if this function is continuous, then the intermediate value theorem states that every single value in between these y values, there will always exist an x value that points to it, because it would be impossible to reach from here to here and not touch that y value that's in between these ranges if it was continuous. So how can we apply that here? First, what we're going to be doing is finding the values of the endpoints, because here I'm saying that this is one endpoint and this is another, and so all values in between here on the y-axis should be achievable by some x value. So what we're going to be doing here is finding the endpoint values. So we're going to be finding m of 15, we're going to be finding f of 15, we're going to be finding m of 20, we're going to find f of 20. So let's do this. The values for m are much easier to find because they're right here. So m of 15 is 6, and m of 20 is 5. Now in order to find the values of f of 15 and f of 20, we just use our calculator. So I can just start deleting stuff here. I'll delete this. And what we can do is just set a slider here and do 15, 20. So we see that we have 2 and 6.686. So we're going to have 2 and 6.686. And what we're going to be doing from here is calculating the value of d of t at these points. Alright, so what we're going to be doing now is, let's bring this over here. D of 15 is equal to m of t minus f of t. So m of 15 minus f of 15 is 4. D of 20 is going to be equal to 5 minus 6.686. This is equal to negative 1.686. Negative 1.686, and there we go. Now, does this help us at all? Yes, because it's stated here that d is differentiable. If it's differentiable, it's continuous. So because d is a differentiable function, and one of the endpoints is above 0 and the other endpoint is below 0, every value in between must be achievable by some time, some t variable. And since 0 is in between this interval, 0 must be achievable. So, as per the intermediate value theorem, since the function d is continuous from 15 to 20 for the values of t, there exists a value t such that d of t equals 0. And there we go, that's question 1 solved. So let's move on to question 2. Now we're going to be doing question 2. So we have a shaded region S here, which is bounded by the graph of some polar curve. And what do we have to do? First, we have to find the area of region S. So in order to do this question, this is just a formula that I've memorized, and you most likely have memorized it as well. It's just the area of a polar graph. So the area is equal to 1 over 2 times the integral of r squared d theta. And then your bounds are going to be 0 to pi. So in order to do this, remember you have a calculator, use your calculator. So this is 3 plus 2 sine 2 theta plus cosine 2 theta. 3 plus 2 sine 2x plus cosine 2x. And we're going to be integrating this from 0 to pi. We're going to be integrating this from 0 to pi. We're going to multiply this by 1/2. And we're going to have to square this dx. And there you go. That's the answer. 18.064. So we're going to write down area equals 18.064. And the setup for your calculations is exactly what I wrote here. Now on to part B. There exists a point on the curve at which the slope of the line tangent to the curve is -3 over 7. At this point, we have dy d theta, and we need to find dx d theta. Well, this is also really great. Remember that this curve is in terms of x and y right now, meaning a tangent line here, the slope of the tangent line, is dy over dx. Right now, we have dy d theta, and we need to find dx d theta. Well, something that's great is that dy over d, I'm going to write 0 for theta, dy divided by d theta divided by dx divided by d theta. Well, guess what? This is dy over dx. So in order to find dx d theta, all we're going to be doing is plugging in the values here. So we have -3 over 7, and let's write it out here. So we know that -3 over 7 equals 3 root 2 over 2 divided by dx d theta, which is what we want to solve for. So dx over d theta. And in order to find dx d theta, we multiply both sides by dx d theta and multiply both sides by -7 over 3. And if we do that, it's just going to simplify too. If we multiply 7 and 3 here, the 3's cancel out, so you get 7 square root of 2 divided by 2, and this value is negative. Oh, let's put the negative sign here. There you go. So the value of dx d theta is -7 square root 2 over 2. Next question. Find the value of theta in the interval 0 to theta to pi over 2 at which r has a critical point. So how do we find when r has a critical point? That's when the derivative is equal to 0. And again, we have a calculator, so you could just plug it in here. We have 4 cosine 2 theta equals 2 sine 2 theta. So 4 cosine x, is that our function? Yeah, 4 cosine 2x, 4 cosine 2x, and then we have 2 sine 2x, sine 2x. Remember, our bounds are from 0 to pi. So if we look over here, they intersect right here. And our bounds are 0 to pi, so we're just going to do 0 less than x less than pi. And we can just copy the bound here. And if you want, you can change your bounds. So let's just set our steps in terms of pi. And what do we get? So we get that 0.55375, 2.12437. So those are the values we want. Find the value of theta in the interval, from 0 to pi over 2. So this means that we can shrink it even further, and there you go. 0.55357. This is the point at which r is going to be having a critical point, because this is the value of r theta. So for part CI, so CI, theta is equal to 0.55357. 0.55357. Alright, now CII. Use a derivative test to determine whether the critical point is the location of a relative minimum, relative maximum, or neither. In order to use a derivative test to determine the critical points of the function, we can just look at its derivative function. So let's just graph it actually. So 4 cosine 2 theta minus 2 sine 2x. So we're gonna subtract this, and we're gonna set the bound to, let's say, 0 to x to pi over 2. Now, if we look at this function from 0 to pi over 2, and this was our critical point, we can see that just above, this function is positive. So the derivative is positive right before, and right after, the derivative is negative. What does this tell us? This tells us that just before this point, your function is increasing in value. Then right as you hit that point, you start falling and decreasing. What does that sound like? That sounds like a local maximum. So what we're going to be doing is saying the graph of r prime theta. I'm going to use 0 for theta. The graph of r prime theta is positive before, and you can put the critical, so 0 before theta equals 0.55357. That's an extra 0, 55357, and negative after, indicating a relative maximum. And there you go, that's part C, I. Oh, happened. We'll shrink it like this. There we go. And now part D. Find the average distance from the origin to a point on the polar curve for this polar curve from pi over 2 to pi. Now, how can we do this? Well, what is the distance from the origin to a point on the polar curve? Well, it's going to be the actual value of r theta itself. Because if you think about polar curves, the distance to that point is the radius. So the average, so for a given point, for a given value of theta, the distance is r theta. So in order to find the average distance to a point on the curve, we find the average value of the function r of theta. So in order to do this, what we're going to be doing is we're going to integrate r of theta across its bounds. So we want to integrate from pi over 2 to pi. But then we want to divide it by 1 over the subtraction of the bounds. So pi minus pi over 2 is pi over 2. So this is going to be 1 over pi over 2, which is 2 over pi. And this is your answer. But we have to actually compute this, and we have a calculator, so let's do it. So 3 plus 2 sine 2 theta, we have it right here. So what we're going to be putting in here is pi. We have pi over 2. No need to square the function. So let's move this. And we're going to be multiplying this by 2 over pi. And what you're going to see here is that 1.7267 is your answer. So that's the average distance from any point on the polar curve. No, that's the distance from the origin to a point on the polar curve. The average distance is 1.7, was it 726? Yes, 7267. And did we do this correctly? Let's just double check. We did 2 over pi times the value of the function r theta, 2 sine 2x, cosine 2x, correct. And that's question 2 done. On to question 3. A pie is taken from a hot oven and put on a table, and we have the internal temperature of the pie at t minutes after it was taken out, and it's modeled by some function h that satisfies this differential equation, where h of t is measured in degrees Celsius and h of 0 is 75. And we know that for all times above 0, the value, or the temperature, is always above 20 and below 75 degrees Celsius. Now part A. Explain why the following could not be a slope field for this differential equation. So let's see. We know that h of t is always positive from 20 to 75. And what's wrong with the slope field? Well, let's look at the equation itself first. For any value of t, we know that h of t is going to be positive because it's above 20, and then anything above 20 minus 20 is a positive value. But then we have a negative value on the outside here. So we have a negative times a positive being a negative. So this would mean that we would expect the slope field at every point to be negative. But if we look at this slope field here, can you notice something? It's positive. It's the complete opposite sign of what we would expect. So this could not be a slope field because the slope field for this differential equation here should always be negative, because at every single point you have a negative slope, but here you always have a positive slope. So that's your explanation. We can just write here the slopes, the value of dh dt for the given differential equation is always negative in our given interval, but the slope field below shows a positive slope at every time. And there you go, that's part A. Now part B. Find the slope of the line tangent to the graph at h at time t equals 0. Show the work that leads to your answer. So find the slope of the line tangent to the graph at h at time t equals 0. So we have the differential equation here. So we know that the slope of the line is given by this dh dt. So we have dh over dt equals negative 1 over 15 times h minus 20. And recall that at the start we were given the value of h of 0. So we know h of 0 is 75. So all we have to do is plug that in. We have 75 here, this simplifies to 55, and this simplifies to negative 55 over 15. Divide both by 5, you get negative 11 over 3, and that's your answer. The slope is negative 11 over 3. That's the slope of the line tangent to the graph at h at time equals 0. Now let's do part C. So it can be shown that d squared h over dt squared is 1 over 225 times h minus 20. Now remember, we know that h of t is always going to be greater than 20, so h minus 20 is always going to be positive. So the second derivative is always positive, meaning our function h of t is concave up. And we use the line tangent of the graph at h at time t equals 0 to approximate h of 5. Is this approximation an over or underestimate for the actual value of h of 5? Now this is going to be an underestimate because, let's draw a straight line here. If we look at a concave up graph, what we're saying is, let's say time t equals 0, right? Or we'll just pick some time that's before the actual time. When you draw your tangent line, well, the rate of change starts increasing. So now you're always going to be under the curve. You're under what the actual value is. So let's say you're here. Well, now at 0, you're way under. Your approximation is much lower. So therefore, this approximation is an underestimate. Why? Since the second derivative of h is always positive in our given interval, the graph of h is always concave up, meaning that our tangent line at t equals 0 will be under the graph at t equals 5. Fantastic. So now we're going to be doing part D, which is using a separation of variables to find an expression for h of t. So let's get to it, where we have dh over dt equals negative 1 over 15 h minus 20. Now, in order to do separation of variables, we have to isolate the variable h on this side. So what do? We divide both sides by h minus 20. So we're going to bring this over here. And we're going to multiply both sides by dt. So we're going to get negative dt divided by h minus 20 here. So we have dh over h minus 20 equals negative dt over 15. Now we integrate both sides. So we can write it out here. We have dh over h minus 20 equals negative dt over 15. Now integrate both sides, and this is just going to be the natural log of h minus 20. So h minus 20. And then this is going to be simply negative t over 15. And remember your plus c. And now you want to take the natural, you're going to take e to both sides. You're going to raise both sides to the power of e. So this gives you h minus 20 equals e to the negative t over 15 plus c. And you want to add 20 to both sides. So this is what you get as your final answer. You get h as a function of time is equal to this. But remember, we have a given initial condition. H of 0 equals 75. So let's solve for this. If we have so we're going to do h of 0 is 75. That means 75 equals Now e to the negative t over 15 plus c, well, when t is 0, we just have e to the c. So we have e to the c plus 20. And if we just subtract both sides by 20, we get e to the c equals 55. Now, if we go back to our original equation, we can actually rewrite this as e to the negative t over 15 times e to the c. And remember, we just solved for e to the c. So this effectively just becomes 55 times e to the negative t over 15 plus 20. And that is the equation for h of t given the particular solution h of 0 equals 75, the initial condition. And there we go. On to question 4. Let f be a twice differentiable function on this closed interval, and this is the graph of f prime. So for x is greater than 0, you have some function g, which is g of x equals f of x minus ln x. Find g prime 2. Well, that's easy. To find g prime 2, it's f prime of 2 minus, now the derivative of the natural log of x is just 1 over x, and that's just going to be 2. So what's f prime of 2? 1.5, so write it as 3 over 2. And then we have 3 over 2 minus 1 over 2. This is just 2 over 2, which is 1. G prime of 2 is 1. So now on to part B. Find all values of x from 0 to 3 such that the graph of f has a point of inflection. Now remember what a point of inflection is. Point of inflection is when the graph changes concavity. So it goes from concave up to concave down, or concave down to concave up. And what determines concavity? That's the second derivative. A positive second derivative means concave up, a negative second derivative means concave down. So let's just look at our graph over here. If we're changing, and remember this is a graph of f prime, so the derivative of this gives you the second derivative. So when this slope here changes sign, that's when we know that we found a point of inflection. And when does that happen? That happens at the peaks, the local minima or maxima of the graph of f prime. So here, if we look, we see that we have a positive slope, and then we transition into a negative slope. So we know that there's one value of x here that has a point of inflection, x equals 1. And I'm making the assumption that this is referring to a peak, a local maximum. Next, we're going down, 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 so a continuous negative slope. We have a negative slope. And then here, we transition into a positive slope. But this happens at x is equal to 3, so we're going to disregard it. The value of x such that f has a point of inflection is x equals 1. Since the second derivative of f changes sign from positive to negative. And there we go, that's the answer for B. Now part C. From negative 4 to 4, on what open intervals, if any, is the graph of f increasing and concave down? Give a reason for your answer. Okay, so let's see what we have to do. We need the criteria that the graph of f is increasing. So this means it has to be above because this is f prime. You need a positive f prime value. But it has to be concave down as well. What does this mean? Concave down, remember we were just talking about it in part B. Concave down is when the second derivative is negative. So the only point at which you have a negative second derivative is here. Because here this is also concave down, but the graph of f is decreasing, not increasing. So the only range is going to be from 1 to 3. So the range is going to, your open interval is going to be 1, 2, 3. Since f prime is positive, which means increasing, and f double prime is negative. And there we go, just from 1 to 3. And part D. For negative 4 to 4, find the value of x at which f has an absolute minimum and the value at which it has an absolute maximum. So this is the value of f prime. In order to find the value of f, what we're going to be doing is just taking the integral. We're going to integrate under this area. This area represents the relative amount that we can get to f. And we have an initial condition here, which is great. But how do we find out what the absolute minimum or absolute maxima are? So in order to solve part D, we can just look at the values of f prime. You can see here that f prime is negative, meaning your function is literally decreasing in value. So you're not going to be expecting a maximum here. But here, your function f is always increasing. F prime is always positive or 0. So this means that you would, since you're always increasing here, your maximum value is just at the end of this interval here. So absolute maximum at x equals 4. But when's the absolute minimum? Well, as we said over here, your absolute minimum is when you've decreased in value as much as possible. That's just going to be in this small region here, which is when the first derivative is below 0, negative, you're decreasing. And that region is going to end at -2, so absolute minimum at x equals -2. Alright, on to question 5. Let f be the function defined by the cube root of x minus 1, and let g be the function, defined by g of x equals e to the -2x plus 4. The graphs of f and g intersect at the point 2, 1. Let R be the region bounded by the graph of f, the x-axis, and vertical lines. Alright? Evaluate from 1 to 2 of f of x dx. So, what is f of x? It's just this region. That's it. So if we're going to be integrating this, then all we have to do is integrate... Oh, actually that is all we have to do. So to integrate this function, we're going to draw over here. Let's do the integral of from 1 to 2 of x minus 1 to the 1 over 3. And to make integrating this easier, let's just use some u substitution. So this is dx. Well, I'm going to change out x minus 1 to become, let's say, u. I'm going to make this u equals x minus 1. Then we just know du equals dx, so I can swap them out however I'd like. But we also have to change the bounds of our integrand. So if we plug in the bounds here, from x minus 1, if we plug in 1, u is 0. If we plug in 2, we get u is 1. So our new integral is just going to be from 0 to 1 of u to the 1/3 du. And that's it. So this is just going to be, use your power rule for integration. You add 1, then multiply 1 over. So we have 4 over 3, so it's going to be 3 over 4 times u to the 4 over 3. And then you just plug in 1 and 0. You know when you plug in 0, it's going to be 0. So your answer is just going to be 3 over 4. That's it. And if you want to double check your answer, let's just plug it in here. Well, you can't do this during the test because you're not allowed to use your calculator, and you would get in a lot of trouble if you did so. But I'm not taking the test right now, so I can do this. And there we go. We see that the answer is indeed 0.75, which is 3 over 4. That was pretty simple. Let's do part B. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid generated when region R is rotated about the x-axis. Okay, so we're rotating R about the x-axis. How can we think about generating a volume for this? Well, you may have learned about two methods, the shell method and I actually forgot, I think the cylindrical method or the disk method. Anyway, what's the easiest thing that we can do? We know the value of f of x at every single point here. So if I did a drawing, we would know a radius, if we wanted to call it that, at every single point here. That's what f of x is. So if I know the radius of my disk at every single point, what if I stacked up all of these disks? So what I'm going to be doing is I'm going to be integrating pi r squared, that's the area of a circle, pi r squared, and what are we going to be doing? We're going to be integrating over this height region. So from 1 to 2, we're going to be integrating pi r squared. And what is r squared? R squared is going to be f of x. So it's the integral from 1 to 2 of pi f of x, let's write this, f of x squared, and dx. And that's what the volume is going to be. Because from 1 to 2, you're going across every single x value here, and you're adding up every single small disk that exists. And what's every disk? Every disk is an area, has an area of pi r squared. What's r? It's going to be f of x squared. And you should probably plug this in, so you're going to get the integral from 1 to 2 of pi x minus 1 to the 2 over 3. But that's your answer. Next, write but don't evaluate an expression involving one or more integrals to give the perimeter of the region R. So the perimeter of the region R is this. Now, how do we find that? So what are some obvious things that we can find here? We have 1, 2. This is pretty easy. It's just 1 plus 1. So the perimeter is going to be 2, and this is where it gets tricky. You need the length of this. And you may have learned in your class how to find the length of a curve. The length of the curve is going to be the integral of, so you're going to be doing the integral of root, it's going to be this thing, so it's going to be f prime of x, f prime x squared plus 1 dx. And it's going to be from 1 to 2. That's how you would find the perimeter. And remember, you actually have to compute f prime of x. And what's f prime of x? You have, let's just write it out here. We have f of x equals x minus 1 to the power of 1 over 3. Using the power rule that we are all familiar with, we're going to get 1 over 3 times x minus 1 to the negative 2 over 3. And there you go. That's your answer. And if you wanted to apply the squared, you get negative 4 over 3. So that's part C. And part D, evaluate the integral from 2 to infinity of g of x dx. Alright, what's g of x? We have e to the negative 2x plus 4. So you can actually simplify this and write e to the 2x, so e to the negative 2x times e to the 4. And e to the 4 is a constant, so let's just pull that out. E to the 4 from 2 to infinity dx. And then we can think about integrating this. And if you want to do some u substitution, you can. But I'm just going to integrate this directly. So we're going to get e to the 4 times, and the integral of this is going to be negative e over negative 2. So it's just going to be e over negative e to the 2x divided by negative 2. And the way you can just quickly double check this is take the derivative. So you're going to be doing e to the negative 2x times negative 2. That gives you this. So this is going to be from 2 to infinity. Now, let's do the first bound, the infinity. We have e to the negative 2x. Now remember, you have a negative exponent, so this is going to be the same as 1 over e to the 2x. Now what's 1 over e to the 2x as x goes to infinity? This is going to be a fraction with an extremely large denominator, which gets closer and closer and closer to 0. So we can basically say this becomes 0 minus, and remember there's a minus here, so it just becomes a plus. We have e to the 4th times e to the negative 2x. We'll plug into e to the negative 4x, or e to the negative 4, divide by 2. Now e to the 4th times e to the negative 4th, well, that becomes e to the 0, and e to the 0 is 1, meaning your final answer is just 1/2. And there you go, 1 over 2. This is fantastic. And now we're on to part 6, the final question. For x is greater than 0, the Maclaurin series for g is an alternating geometric series. Find the value of g of 3 and show the work that leads to your answer. Well, if we have a geometric series, we can quickly recall the formula for the sum of a geometric series. And it's going to be a of 0 divided by 1 minus r. And a of 0 is the very first term in your sequence, and r is the common ratio. So if we look over here, if we plug in g, if we plug in 3 for g of x, you're going to get negative 3 over 5 as your common ratio. So we know r equals negative 3 over 5. But what's your first term? In order to find your first term, you just do n is 0. So if n is 0, it's just going to be 2. So all you're going to be doing is 2 over 1 plus 3 over 5. 1 plus 3 over 5 is 8 over 5. And this evaluates to 10 over 8, which becomes, divide by 2, you get 5 over 4. And there you go. The Maclaurin series of g of 3 becomes 5 over 4. Alright, part B. The function f is defined by f of x equals g prime x. Write the first 4 non-zero terms of the Maclaurin series for f. Well, this is very easy, actually. All we have to do is take the derivative of each individual term. So this is, I can actually write it out here. So the derivative of 2 is 0, The next one is just going to be negative 2/5. The next one is going to be plus 4 over 25x. The next one is going to be minus 6 over 125. 6 over 125. 6 over 125 times x squared. And then finally plus 8 over 625 x cubed. And if you want to quickly double check, you just go through everything again. So times 4 times 3 times 2. So we have times 4, which is 8, times 3, which is 6, times 2, which is 4, and we have x squared, x cubed, and this is correct. This is the function f of x, the first 4 non-zero terms of the Maclaurin series for f. Alright, on to the next question. The second degree Taylor polynomial for f about x equals 0 is used to approximate f of 5 over 2 as negative 3/10. Justify this. And for this, you can just use Lagrange error bounds. So this is going to be finding the next term. So the Lagrange error bound states that your approximation is always going to be less than, like the difference is going to be less than the very next term. So what do we have? We have the second degree Taylor polynomial for f about x equals 0 is used to approximate 5/10 as negative 5/2 as negative 3/10. So let's see what happens when we start plugging in terms. So we have negative 2/5 plus, let's plug it in, 20 over 50. And if we scale this down by dividing by 10, we get, so if we scale this down, you just get 2 over 5. So this becomes 0 already. The next term we have, let's put in 5/2, we have 25 over 125, this becomes 1/5, times 6 over 4. So we get 6 over 20. And remember, it's a negative. So this becomes negative 6 over 20. And conveniently, we see that this becomes negative 3/10. So what we can see is that we took this value for the approximation because these two canceled out. So we stopped at the third term to get the approximation as negative 3/10. And we have to justify that it has to be less than 1/5. Well, let's find the next term. That's all you have to do. Plug in 5/2. So you're just going to get 125. So when you plug in 5/2 and cube it, you're going to get 125 divided by 8 multiplied by 8 over 625. Now remember that 125 times 5 is going to be 625, and 1 over 8 times 8 is just 1, so this becomes 1/5. And there you go, that's your answer. So as per the Lagrange error bound, so we took the nth, we did the approximation up to the nth term. So we took the approximation up until the nth term. Therefore, we know that the difference of this approximation from the nth term, difference of this approximation from the actual value of f of 5 over 2 is less than the value of the n plus 1th term, which is 1 over 5. And that's your answer for part C. And finally, we are using part D. The function h is defined by h of x equals 25gx minus 2g to the x. Write the first 3 non-zero terms of the Maclaurin series for e to the x. And in order to do this, I guess you could derive it on the test, but what most teachers do is they tell students to just memorize common Maclaurin series. And if you're watching this to try to prepare for the exam, this is a strategy I would highly recommend. Just memorize like sine, cosine, arctangent, e to the x, ln 1 plus x, I believe, 1 over 1 minus x. Memorize all of these Maclaurin series. So what is the Maclaurin series for e to the x? This is simply just 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. We just want the first 3 non-zero terms, so this is it. 1 plus x squared over 2. And now we have, write the first 3 non-zero terms of the Maclaurin series for h. What is h? We have 25 times g of x minus 2 e to the x. So I'm just going to scale everything by 2 here. And all we're doing is subtracting 25, so the first 3 non-zero terms. So this is 50, so we're going to write 25g of x equals 50 minus 25 divided by 5 is 5, so minus 10x. And then just plus 2x squared. Let me just double check that this is correct because we have 25, so 50 over 5. Yeah, so this is going to be minus 10x plus 2x squared. And all you have to do now is subtract these terms. So we're going to do 48 and minus 10x is minus 12x plus x squared. And that's it. These are the first three non-zero terms in the Maclaurin series for H. Because this is the Maclaurin series for G, this is the Maclaurin series for 2e to the x. And that's all you have to do. We've reached the end of the exam. If you have any questions, let me know in the comment section down below. Otherwise, goodbye.